Hi everyone, I'm back with another video. In this video, the purpose of this video is basically tell you a little bit about EBG structures and Eigenmode simulation and dispersion diagram. So there's a lot going on in this video, but take as much as you need from it, or I don't know, maybe you're just curious, right? So yeah, if you're just curious like me, just go through the video. Some parts of it might be slow, some part of it might be fast. Do it at your own pace, basically. So I found a paper on an EBG structure, basically, and then they simulated this on basically this unit cell that you see here. They propose it actually as an EBG structure, which is like a band gap structure, right? You might see that in your Google search, or you might heard of these structures. What do they mean? What's their application? Stuff like that. Basically, you can read more about it. But just because I wanted to have a practical video, basically I went and looked for this structure online, and then I found the paper that proposed this. Unfortunately, I don't have the paper. I'm sorry to the authors, but the structure seems to be simple enough for us to go through, right? So here we have a square unit cell that has about 3 millimeter on each side, and then it's 2.2 millimeter thick basically it has dielectric slab. It's a RT6010. I don't remember the permittivity, but it's one of the materials in the library, so we can go through that. And then it has a metallic patch with 2.4 millimeter on each side again. On the top layer, it has a via with 0.5 millimeter of radius. And then on the back, it has a ground as well, right? So we were gonna simulate this structure, simulated using Eigenmode tool on Ansys, and basically look at the different frequencies that are the eigenfrequencies of this structure, right? And then using the dispersion diagram, hopefully we will see the gap that is supposed to be in the frequency spectrum of this structure, and then we would understand why the authors of the paper that I forgot to mention basically used it as an EBG structure. Okay, so keep this. You can already see I have some stuff written here as well. I'm going to explain these to you later. But for now, let's just go to the physical labor of basically making the CAD model of this in Ansys, and then we continue with the rest of it. Okay, so I already have this one here. What I'm going to go and do is make a new project. Okay, and then I'm going to insert an Ansys HFSS simulation here, right? And then what I'm going to start with is the dielectric slab. So I need a cube looking like this. If you forgot, what I can do is for a second, I thought I don't have, I'm not sharing my screen, but I am. Okay, so here, nope. Okay, so good, right? So we need about 3 millimeter on each side, so 1.5 millimeter minus 1.5 millimeter, and then 2.2 millimeter as the thickness, 3. I should have 0 this. So this is the 0 one. Okay, apply. Good. So this is our dielectric slab, right? And I want to make it transparent so we would see what's going on. And then I don't like the grid either, so I remove the grid. Then we need a sheet as our patch on the top. So that's about 2.4. So it's going to be minus 1.2 millimeter, minus 1.2 millimeter, and then 2.2 millimeter on the top. Again, if you're familiar with these sides of the HFSS, just fast forward it, honestly. Then because this is metallic, I'm just going to apply perfect E to it. Okay. Then I like the metallic ones to have a gray color so I can see the difference between this structure and the other ones, right? And then I know that there is a ground on the bottom, right? So what you can do is try to make a new basically patch on the bottom exactly the size of our dielectric, and then apply perfect E to it, perfect electric field to it, perfect electric boundary condition to it, or you can press Alt, rotate this, and then press F. That would allow you to choose this phase. If you don't know, if you're not listening to me, so you can go to selection mode, choose phases. As it says, if you can press F, it would allow you to do that, right? So then once you do that, then you can choose this one and then say perfect E. Okay, does the same thing. Then we're gonna rotate this back to its original state. We're gonna do this, bring it here. Then we need the cylinder. Okay, so then we know our center is 0, 0, 0. The height is exactly the same height of this guy, the dielectric, and then our radius was 0.5 millimeter, right? Okay, now that we've done this, we need to apply perfect E to this, right? So I'm going to go back to choosing face. No, actually, I'm going to go perfect O and then perfect choose object. I don't know why I say perfect. Then F and then choose the boundary of this guy and then say perfect E. Remember in perfect E boundary condition, right? You can just choose the sheet and do it, right? So it doesn't have to be a bulk. So that way you can simplify your simulation. Now we need kind of like boundary condition around this unit cell. So the unit cell is done, right? Now we need a box around it that would allow us to say this is an infinite array, for example. That's very common to simulate basically unit cells with. So we're going to make an infinite array of this unit cell by using primary and secondary boundary conditions. And I have to make this much higher. So for example, we can choose 15 millimeter, right? Large enough. Depends, it really depends like on the lowest mode that you might have, like in the basically, yeah. So it has to be about lambda over 4, the lambda being the largest wavelength that you have in this structure, okay? So for now, because I don't know what eigenfrequencies I have here, I'm just gonna make it a large one, right? And then we can apply wireframe to this so that we don't see it, okay? And then we're gonna choose this face up on top of it because I know that my structure is infinite in X and Y direction, right? If you don't know about these, the primary and secondary conditions, I have another video on infinite array of unit cells, so you can look at that one. Then here on the top, we basically have the excitation coming. So in order, in Eigenmode simulation, we don't actually have an excitation, we don't have to assign that. So what we can do is to go to PML setup wizard, and then I don't choose, it's just set default formula. Minimum frequency, I'm going to say it's 1 gigahertz. Again, it depends on the minimum frequency. So I'm just going to choose that. So on the top now, I know that I have a PML here. Here, it just came, right? So it means like an absorber, similar like an absorber. Then, in order to make this an eigenmode simulation, we come here, choose eigenmode. Super easy, right? It became eigenmode. Then now we need to make sure that Ansys understands that this is not an isolated unit cell. It's going to be surrounded by similar unit cells, right? So again, we're going to go do that primary and secondary, basically boundary conditions, okay? Before doing that, let me go back here because now this is related. Because here, when we want to assign these boundary conditions, we can assign a phase delay between the primary and secondary, okay? Why do we want to do that? Because these phase delays basically it would allow us to define the propagation constant or the basically propagation vector, which you can see here is the formula is for it in a 2D structure, it has two directions. It can be in kx and ky directions, right? So we can have the vector, the propagation vector, somewhere that is the combination of both kx and ky. And think of this kx and ky as phase delays or phases that can be applied in x or y direction, right? So once we do that, there is this French physicist, I hope I'm not butchering his name, which I'm going to do though, Brian, I don't know, zone, that would basically allow you to take care of the area that actually matters for this vector network. So this zone, I'm not going to repeat it. I feel too embarrassed to do that. But it says in order, so after you apply the phase delays in x and y direction and basically define kx and ky, in order to capture all the combinations that can happen, and also make use of, this is a key factor, make use of the symmetry in this unit cell. All you need to simulate is basically 1/8 of this square lattice. Moving from gamma to x, meaning that only kx vector is changing, or moving from point x to m, which means only ky is changing, right? And then from m to gamma, which is x and y changing. X and y simultaneously changing, okay? If you cover this area, simulate in this area, then using symmetry, which is, again, our structure is symmetric. We wouldn't be able to do this if it wasn't. But since it is symmetric, we can use this zone and then simulate only 1/8 of this vector network, vector space to make sure that our dispersion diagram is going to capture everything, okay? So first thing first, what we're going to do is assign primary and secondary boundary conditions. Second thing is that we're going to apply some phase delay between secondary and primary in each direction, x and y. And then we're going to simulate, I'll show you how to simulate this 1/8 transitions, or these three transitions from gamma to x, x to m, m to gamma, okay? So let's go. Let's see what we have to do here. First, as we said, we're going to go primary. So we're going to assign a primary boundary condition here. So we go primary. And then the u vector, I usually just use in the same direction. So x, good. Then we need to rotate this a little bit. This is our secondary. So assign boundary coupled secondary, and then we're going to use our primary as a linked one, new vector. Okay, and then next, it's going to ask for phase delay. Okay, so remember, our vectors are in x direction. Our phase delay, though, it's in y direction. So I'm going to call this phase delay y, okay, py, because the phase delay between them is going to be in y direction. For now, I'm going to apply 0 degree. Okay, then let's rotate this. The other side, we'll do this one. Sign boundary, coupled primary. Then y. Right in front of it, the other boundary is going to be secondary. This is our primary 2. Be careful about that one. And you go here. So make sure in these primary and secondary boundary condition, make sure both of these red and blue arrows are lying on the surface that you choose, okay? I usually go with the positive, from the negative side to the positive side. That would make sure that my vectors are going to basically lie in there. And like you can also choose reverse direction if it doesn't, right? So you can do that. Then the other phase delay is px, because now we are orthogonal to the px direction. Again, we're going to choose 0 here. Okay, perfect. So the plan was we define primary, secondary. We have our boundaries here. Primary and secondary is here, and then primary 2, secondary 2, right? So be careful that each secondary has to be in front of the primary one, so they're in the same basically direction. Now we're going to go to the analysis, make a simulation setup. So it says minimum frequency 1. I'm going to set 9, so I set it to 1. Maximum number of passes, I'm going to say 20. And in order to see the gaps between the frequency, these modes are basically the eigenfrequencies of the structure, right? So if you set 1, it's going to simulate the first frequency, the fundamental frequency for you, and you're not going to be able to see the gaps between this frequency and others, or the gaps in higher frequencies. So you need to increase this. I'm going to set it to 3, for example, so that I can see 3 eigenfrequencies of this structure. Okay, and then this is okay. And I'm going to save this as Eigenmode 3. As you can see, I've done some practice before. So we said here, we said we were going to simulate this. We are going to go, and as I said, px or py are similar to our kx and ky here, except some factor, right? Which is the unit cell period. So we don't care about that. So all we need to do is transition from gamma to x, we need to change px, while py is 0. So I'm going to say our point gamma is px and py are 0. Okay. Our point x is px is 0, py is 180 degree. Okay, and I know it's messy. I don't have my tablet right now. So x, and then we're going to go to point M. So point M is px and py are both 180 degree. So as you can guess, and then, okay, and then we go back to gamma, which is px and py are 0, and then yeah, so then that's it. So from gamma to x, in order to simulate this as we have to translate it to Ansys, right? So we need to keep px to be 0. Am I saying that right? No, I think I made a mistake here. So sorry. So py is still 0, px is 180. Okay. So in order to go from gamma to x, we need to keep py as 0, px is 180. Okay, perfect. So let's go transition, parametric, add. So px goes from 0 degree to 180 degree. You can go with a step of 10 degrees, 15 degrees, whatever the smoother the transition, it makes your dispersion diagram smoother if you go smaller step, right? So remember, this is going to be hard, so I'm going to go with 15 for now, because you see that the finer you go, the labor after it's going to be harder. So px is 0, and then I'm going to keep py as a single value of 0 degree while this is happening. Okay, you might say, oh, you already set py as 0 as the default, so why are you doing that? Just to be sure, no other purpose. Okay, so we add this, and I'm going to call this guy gamma to x transition. Okay, then the second part of this was from point x to m, right? So we need to keep px as 180 while py goes from 0 to 180. So we're going to do that. So py goes from 0 to 180 with the same steps of 15 degrees, while px has a single value of 180. Okay, and then, okay, so this is our point x to m. Third part is m to gamma, okay? But remember, this is a line that is x and y are, sorry, kx and ky are exactly the same, right? So we have to make sure that px and py, both of them go from 180 to 0 degrees simultaneously. How do we do that? We come here, add a parametric. So we say py, right, goes from 180 to 0 degree with 15 degrees of, okay, sorry, it doesn't let me. So we're going to take care of it after. And then px has the same thing, right? What we're going to do is we're going to choose both of these and then sync them. That would make it, if you go to the table, you can see now px and py, but they're both changing, but they're changing at the same time, right? If you don't sync them, if you go to the table, now you have so many more cases because it's going to count when px is 0, py goes from 0 to 180, and you know the story, right? So we have to sync them to make sure that this change stays on the straight line with 45 degree, basically. So this is going to be our point M back to gamma. Okay. So now all we need to do is simulate this. So I'm going to analyze all. It might take a couple of minutes, so I'll pause the video. Oh man, that's taking forever, okay? So I wanted to mention a couple of things. You see the pass number here? This is the last of the optometric analysis that I have, and it says solving 1. So notice that because I increased the number of passes here, I set it as the maximum number of passes 20. So it's gonna go up to 20, and then if it converges up to 20, fine, it stops there. Like it might stop at past 11, 12, right? Or if it doesn't, it's going to go to past 20 and then it's just gonna give up, right? And then, so now it's finished. But it said solving 1, right? So you might be able to make this simulation faster if you have the license for it, okay? Here on tools, you go to options and then HPC analysis and analysis options here. You can edit this and then say number of variation to distribute, right? So you can increase this, especially if you have the number of cores for it, like to 3, 2, or 4, for example, depending on your computer, your device, you can do that. And then, for example, if this one has 13 different variables, it's going to try to solve 4 of them at each time, right? So if one of them finishes, it's going to go to the next one. So it makes it much faster, as you can imagine. And also, don't always trust Ansys, okay? So we're going to go here, okay? I think I made... Okay, so anyway, it's going to say, it's saying like it has, right now my simulation has 3 modes. Mode 1, 2, 3, about 9.71 gigahertz, 9.72 gigahertz, and then the Q factors for them too, and then 12.4998. Basically frequency. So these are the 3 modes that I wanted, right? Now look at the convergence here. If you plot this, okay, it got the convergence, right? Some prefer to basically, because this is going to stop as soon as it gets below the threshold, right? Some people like to make sure they would go here in options and it says minimum number of converged passes. If you increase this, then it's not going to be happy when it reaches 1 convergence. It's going to try to get 2 or 3, right? Because sometimes this is just an accidental convergence. Again, if you really care about the accuracy, you might be able, you have to change with these. For example, this is another option. Right now we got, on the 4th pass. I'm going to try to find something that didn't converge right away. Okay, yeah, you can see here. You see, like here, actually this converged too. Anyway, so what I'm trying to say, because I noticed some of them went to about 20 passes and it stopped because the maximum number of passes was 20. But it says here converge, right? For some of these variables, it might not converge. So you might have to go increase the number of passes and then run the analysis again to make sure that it's always converging. Again, it depends like what type of accuracy you're looking for. For our simulation, it's fine for now. So in order to see the results, we're going to go to results, Eigenmode, parameters, report, rectangular plot, and then eigenmodes. We have 3 modes, so I'm going to get all the 3 modes, and I only care about the real part of this frequency or the mode, which is the frequency. So I'm going to choose real, and then PY or PX, it's fine. You can choose that, new report. And it's going to get all the combinations, right? This looks nothing like a dispersion diagram. So what we're going to do is extract all the data that we have for these 3 modes and then make our own dispersion diagram. So right now, Ansys doesn't have this, so you have to do this manually. Eigenmodes plot 1. Let me just make sure that I don't have anything in this name. Okay, Eigenmode plot 1. Then we are going to go and so, okay. So here, if I go and open this one, okay, so you can see for each of these PY, PX, all of these, it's showing us what was the real value of mode 1, mode 2, right? So what we need to do is to make these transitions happen. So remember we said we're going to go from gamma to x, x to m, m to gamma, right? From gamma to x, px was going from 0 to 180, py was 0. Let's find that. So that's exactly, it's not exactly that. So we have p, okay, so I'm going to choose that. I'm going to choose these three, copy them here. This is, I'm going to call this point. Point gamma was when point x and y were both 0. So I'm going to copy this here. Oops, I should have copied these three too. So I'm going to copy these three of them. Okay, the next one is px and py. So px is going to increase, and then the same thing, while py is 0. So it's a little bit of pick and choose. So you have, yeah, we have to do this to make sure that we get the right transition. So then we have this one. So remember I said like you can make the step of px and py like finer. You can go to even 1 degree, but then remember that this step is going to be much harder because now you have to choose, you have to pick and choose with 1 degree basically. So py is 0 and we are doing this. We are getting there. You can fast forward this point, but basically we're going to go till we get to px being 180 and py being 0. This is our point. So px being 180, py being 0, that's point x. So I'm going to call this point x. Now we have to move from point x to point m, which is px, and px remains 180, py goes to 0. So we have to find the points that px is 180, and then py goes to. So we already have this one here, just to make sure, yeah, if you can see here, this is a repeat, right? So we don't need to take this. So I'm going to go and do this, right? Px is 180 and py is going to 180, from 0 to 180. Now we got to 180, 180. That's our point M. So we're going to call this point M. And next, what we have is px and py. Both of them are going from 180 to 0. So we have 180, 180 here. We need to find 165, 165, which is here. Then 150, 150. The same thing here. Then here. I know it's very annoying that Ansys doesn't do this on its own. I hope I'm not missing anything, but should be fine. Okay, we're almost getting, so we're gonna go back to point gamma, which is 0, 0, right? So we're gonna continue this till we get to that gamma point. Almost done. So we're gonna go to 0, 0. And this is our point gamma. Now point gamma, if you draw this, like if you plot this, it's going to start from somewhere up there, right? The frequency is up there. So usually in order to see the line of light, they make all of this 0 for point gamma so that they can see that line of light. And then the same thing, because this is the same, exactly the same point. Now, you're like, okay, still we don't have a straight line for our x-axis. How do we do that? So we're gonna go by 15 degrees till we get to 540 degrees, okay? So I'm going to do that. And then now angle. So all we need to do now is to get this x-axis and these three y-axis and then draw them. Okay, so as you guessed, mode 1 and mode 2, they were very similar, but you can see here, this is actually, am I making a mistake? Which modes were they? So I went and looked at my other simulation that I did before, and there I thought this would be interesting because it shows like what can go wrong in the simulation. So here the box size I used was about, not this one, the vacuum box I used was about 20 millimeter instead of 15 that I used before, right? And then I set up the same simulation, and then the only thing was that that I used for PX and PY steps change, I used 10 degrees. So I repeated exactly the same thing there, and then or made this dispersion diagram. And now you can see that things are much better. Mode 1 actually here, and mode 2 and mode 3 are much more separated, and you can actually see the gap between them, the frequency gap between them. So this is much better, I think. I have to make sure that these values, yeah, the values are different. So just wanted to let you know that in case that happens, you have to be careful about the box size because it impacts the minimum frequency of the structure. Yeah. So yeah, that's it.